Late July 1944. The Bocage country of Normandy. Through the magnification of a Carl Zeiss optic, a German anti-tank gunner watches greasy black smoke rise. Their logic is completely sound. In their own army, replacing 5 heavy combat vehicles requires a monumental, months-long effort, manufactured by completely different civilian corporations across the United States. The mechanics in the mud had just stripped an M4A, one built by a locomotive company in New York. The damaged tank waiting for repair in the adjacent field was an M4A3, built by an automobile manufacturer in Michigan, possessing a completely different hull shape and a radically different engine. By standard engineering logic, the parts should not fit. To force the organs of one machine into the body of another should have been a nightmare of mismatched tolerances and custom fabrication, but it was not. A mechanic holding a heavy steel bogie wheel from a locomotive factory in New York stands next to a crippled tank built by an automobile manufacturer in Michigan. To the naked eye, the two vehicles look fundamentally different. The destroyed donor tank features a smooth, rounded, cast steel hull. The damaged recipient has sharp, welded, angular armor plates. They have completely different engines and were assembled by different labor forces hundreds of miles apart. By all conventional engineering logic, the parts should not mate together. Yet, the mechanic hoists the salvaged suspension unit, aligns it against the side of the welded hull, and pushes the heavy mounting bolts through. They slide in perfectly. He torques the nuts down, and the tank is suddenly cured. This was not a stroke of battlefield luck. It was the result of a ruthless industrial mandate enforced long before the first shot was fired. It means waiting for 5 new chassis to roll off a factory assembly line in Kassel or Stuttgart. It requires a vulnerable rail journey across. The American Ordnance Department did not design the Sherman as a singular, rigid vehicle. They designed it as a modular platform built around the religion of strict interchangeability. When the United States mobilized for war, the government knew that a single factory could not meet the astronomical production quotas. Dozens of civilian heavy industries were drafted to build the Sherman. Because of varying manufacturing capabilities, they used different engines, from aircraft radials to massive Ford V8s, and different hull forging techniques. But Washington mandated that the interfaces, the exact points where parts connected, must remain universal. The mounting holes for the suspension were drilled to the exact same fractional tolerances across every factory floor in America. A radio tray extracted from a cast hull tank plugged seamlessly into the standard turret wiring harness of a welded hull tank. A 75mm gun barrel forged in a Pennsylvania steel mill locked effortlessly into a breech block machined in an Ohio tool plant. The track pitch, the sprocket teeth, and the road wheel hubs were geometrically identical across thousands of vehicles. This philosophy, rooted deeply in the American industrial tradition of mass production, changed the nature of frontline combat. It meant that mechanics operating in a muddy French orchard did not need to act as custom fabricators. A bombed-out continent, followed by a perilous road march to the front line. They naturally project this same logistical burden onto the Americans. They did not need a lathe to shave down an oversized track pin, and they did not need to rethread mismatched bolts. The parts simply fit. This geometric discipline created a terrifying battlefield momentum. A Sherman, crippled by an anti-tank mine at dawn, was dragged to the recovery yard by noon. By dusk, its shattered suspension was replaced using the salvaged steel from a completely different tank that had been permanently destroyed the day before. By the next morning, the repaired tank drove back to the front line, its engine roaring, ready to fight again. To the American mechanics, it was a simple, repetitive arithmetic. They traded broken modules for salvaged modules, keeping the maximum number of gun barrels pointed at the enemy. But mechanical aptitude is not a uniquely American trait. Across the front line, German mechanics were equally skilled, heavily trained, and possessed years of hard-won experience repairing armor from the deserts of North Africa to the frozen steppes of Russia. They completely understood the value of battlefield salvage. The mystery deepens when looking at the opposing camps. If a shattered American tank could be resurrected by snapping interchangeable parts together like industrial building blocks, why couldn't the veteran German maintenance crews simply swap road wheels and tracks between their own visually similar machines? On the other side of the front line, in a dimly lit barn serving as a field workshop, a veteran German mechanic faces a maddening contradiction. They assume the United States must build 5 replacement tanks in Detroit, load them onto cargo ships, haul them across 3,000 miles of ocean. He has a damaged Panther tank, immobilized by a shattered final drive. Beside it sits a ruined Panther of the exact same model, abandoned after an engine fire. To the eye, the machines are identical. The mechanic instructs his crew to strip the heavy drive sprocket and transmission from the donor and mate it to the survivor. They spend hours wrestling the massive steel components through the mud, but when they attempt to slide the replacement drive into place, it refuses to seat. The splines on the shaft do not align. The bolt holes are offset by just a few millimeters. This was the artisan's trap. German armored production was driven by a philosophy of continuous, localized perfection rather than rigid, universal standardization. If a German engineer discovered a way to improve a transmission housing or reinforce a track pin on a Tuesday, the factory implemented the change on Wednesday. They did not wait for the rest of the supply chain to catch up. As a result, 2 Panther tanks rolling out of the same factory just 3 months apart might look identical on the outside, but their internal mechanics belong to completely different evolutionary stages. The American system froze designs to ensure every part fit every tank. The German system constantly mutated its designs, sacrificing interchangeability for incremental tactical upgrades. For the highly skilled mechanics in the field, this creeping modification was a nightmare and slowly drive them through the congested beachheads. By all reasonable military calculation, the American offensive capacity in this specific sector should be crippled for weeks. They could not simply harvest parts from a graveyard. They had to act as custom fabricators, filing down gear splines, rethreading bolts, and forcing mismatch tolerances to accept one another. Worse still, the German mechanics were fighting a war against their own suspension designs. To replace a single damaged inner road wheel on a Panther or Tiger tank, a crew had to unbolt and remove as many as 5 outer interleaved wheels. First, it was a brilliant engineering solution for distributing weight for a smoother ride, but a logistical disaster in a muddy trench under artillery fire. The friction extended beyond the wrenches. To cannibalize a wreck, an army first has to move it. While the Americans possessed fleets of specialized, standardized armored recovery vehicles, the German military had vastly outgrown its towing capacity. The standard heavy recovery half-track was designed for the lighter Panzer III and IV. Hauling a 45-ton Panther often required linking 2 or 3 of these unarmored half-tracks together in a highly vulnerable, synchronized chain. When specialized haulers were unavailable, desperate commanders ordered functioning combat Panthers to tow their dead brothers. The immense strain frequently shattered the fragile final drives of the towing vehicle, multiplying the losses. The German maintenance crews were arguably some of the finest combat engineers in the war, but they were trapped in a system that demanded bespoke craftsmanship on a battlefield that required industrial speed. Night falls. The infantry skirmish lines shift a few miles to the east. When dawn breaks 2 days later, The German gunners looked through their binoculars. They were forced to watch perfectly good armor sit idle, waiting for specialized parts that were trapped on bombed-out rail lines, while usable spares lay rotting in mismatched hulks just miles away. The system was paralyzing itself from the inside out. But a military machine cannot simply pause a war to fix its supply lines. What happens to an army's heavy armor when it can no longer easily cannibalize its own wrecks? Autumn 1944. A muddy crossroads near the German border. A heavy Panther tank shudders, grinds, and halts violently in the freezing rain. The transmission has finally sheared its internal teeth under the strain of continuous retreat. The young tank commander looks down the road. He has no specialized recovery vehicles. He has no replacement parts. And the American artillery is already walking high-explosive shells toward their position. They cannot tow the 45-ton machine. They have no choice but to abandon it. But the German doctrine of late-war salvage had degraded from an organized, factory-level process into a desperate, localized scavenging operation. The crew cannot simply walk away. The German supply chain is so starved that these men know their next tank, if the army can even provide, one might be missing critical components upon delivery. In the absence of a functioning logistics network, the crew must become their own supply line. The men scramble over the steel hull at the exact same field. The blackened hulls are gone. There are no charred turrets. There are no shattered tracks, working frantically under the distant roar of incoming fire. Unlike the American Ordnance crews, they are not harvesting heavy tracks, suspension bogies, or transmissions. They have no cranes and no trucks. They can only salvage what a man can physically carry on his back. Inside the cramped, freezing fighting compartment, the gunner reaches into the turret and carefully unbolts the exquisite Carl Zeiss targeting optics, cradling the heavy brass and glass instrument like fragile treasure. The loader wrestles the MG-34 machine guns free from the ball mount and coaxial station, stuffing heavy belts of ammunition into canvas sacks. The radio operator rips out the headsets, the throat microphones, and the delicate receiver units. Knowing that electrical components are becoming impossibly rare in the fatherland, what remains is the vast, immovable bulk of the machine. The heavily sloped armor, the high-velocity 75mm gun, the intricate interleaved road wheels, millions of Reichsmarks and thousands of man-hours of precision engineering. Because the German army is retreating, they are abandoning the physical terrain. In armored warfare, the army that loses the ground loses the wrecks. The American salvage system thrived because they constantly pushed forward, inheriting vast graveyards of usable donor steel. The Germans were falling back, meaning any immobile tank left behind was a permanent, catastrophic loss. To prevent the advancing Americans from capturing the vehicle, there are only deep, wide, muddy gouges in the earth where 30-ton steel corpses have been dragged backward into the tree line. The crew commander initiates the final phase of German salvage, destruction. He sets a standardized demolition charge deep inside the engine compartment, resting it directly on the massive Maybach block. He places a second charge inside the open breech of the main gun. The crew drops into a muddy ditch and covers their ears. A muffled, violent concussion shakes the earth. The tank's hatches blow open, venting a sudden pillar of greasy black fire into the rain. The suspension slumps as the internal blast shatters the chassis. The men begin the long walk eastward, carrying their optics and radios through the mud. The German recovery system had completely collapsed into a primitive survival mechanism. It was no longer a structured effort of field workshops and heavy winches. It was exhausted, crews carrying pieces of dead tanks on their shoulders, hoping to find a working hull somewhere behind the next river. This was the quiet, mechanical hemorrhage destroying German armored strength. But a war is not fought one tank at a time. When the American system of relentless, standardized mechanical harvest collided directly with the German reality of bespoke parts and self-destruction over months of continuous combat, the mathematics of the campaign fundamentally changed. When these two contrasting systems collided at an operational scale, what was the final battlefield result? Later that afternoon, the American armored column attacks the next ridge. The German defenders brace for a depleted force, but the numbers do not make sense. Winter 1944. The Ardennes forest. The temperature plunges, freezing the muddy roads into hardened ruts that shatter steel track pins like glass. An armored division is not just fighting the enemy, it is fighting the earth. Merely driving a Sherman tank 50 miles across this frozen terrain tears up suspensions, burns out clutches, and grinds down transmissions. Even without a single enemy shell fired, a tank regiment bleeds vehicles by the hour. At this operational scale, the true mathematics of the war became undeniably visible. For a German panzer division, a mechanical breakdown in this environment was often fatal. The surviving reports indicate that German heavy and medium tank battalions frequently operated at a 30 to 40% readiness rate. A commander might have 100 formidable Panthers on his unit roster, but on the morning of a critical offensive, only 35 could physically start their engines. The rest were paralyzed, trapped in rear area workshops waiting for specialized parts, or abandoned on the side of the road to be destroyed by their own freezing crews. Across the front line, the American armored divisions presented a stark mathematical contradiction. Despite taking heavy losses from German anti-tank fire and suffering the exact same environmental breakdowns, U.S. tank battalions consistently reported operational readiness rates hovering between 80 and 90%. This was the ultimate battlefield payoff of the American salvage doctrine. The German anti-tank gunner from the opening days of the Normandy campaign believed he was fighting a war of sheer industrial volume. The American armored strength is practically undiminished. The defensive line is overwhelmed by an assault of combat-ready machines operating with coordinated, aggressive precision. He assumed every disabled Sherman was instantly replaced by a brand new machine shipped across the Atlantic. But the ocean was simply too wide, and the captured French ports were too congested to sustain that kind of immediate tactical replenishment. Detroit provided the initial volume, but the mechanics in the mud provided the momentum. The true engine of American armored dominance was turnaround speed. When an American tank threw a track or seized an engine, it did not languish for weeks waiting for a factory replacement. It was dragged into a field shop, fitted with salvaged, standardized parts from a graveyard of write-offs, and pushed back to the front line in a matter of days, sometimes hours. The system was unsentimental, efficient, and relentless. It essentially allowed the American army to recycle its own mechanical casualties. The German military could often dictate the tactical terms of an engagement. They could position superior anti-tank guns in concealed hedgerows, utilizing heavy armor and high-velocity weapons to inflict disproportionate losses on advancing American columns. But those localized tactical victories evaporated at the operational level. A German unit might disable 5 Shermans in a brutal afternoon, only to face 3 of those same vehicles, repaired and rearmed, less than 48 hours later. Meanwhile, any German tank that took a mobility hit from a devastated French field, he counts the wrecks. 1, 2, 3, 4, 5 American M4 Sherman tanks sit motionless in the crushed grass. The German crew, retreating through the hedgerows, assumes they are fighting a limitless tide of brand new tanks, freshly unloaded from a bottomless industrial pipeline, was usually permanently erased from the order of battle. The German army was fighting a war of attrition. They believed they were winning in the crosshairs. while losing a war of logistics they could not fully comprehend. They could clearly see the overwhelming number of American tanks assaulting their lines, but they could not see the hidden machinery sustaining that pressure. The war of production was not just won by the clean, humming assembly lines of Michigan and Ohio. It was sustained in the freezing rain of Europe by men operating under the constant threat of artillery, armed with heavy steel winches. But as the war finally drew to a close, and the vast graveyards of shattered armor were left to cool in the peace, what is the true legacy of the men who fought this shadow war of wrenches and grease? The question in that Norman field in late July 1944 was never really about the penetrating power of a high-velocity shell. The German gunner, looking through his Carl Zeiss optic, was absolutely correct in his physics. He had killed those 5 American machines. The armor was pierced, the tracks were severed, and the immediate tactical threat was neutralized. But his calculation failed, because it relied on an old, rigid rule of war, that a destroyed weapon remains destroyed and that recovery requires a factory. It is the only explanation that fits their understanding of the war, but that explanation was an illusion. He did not realize that the American military did not view a tank as a singular, irreplaceable entity. The true nature of the American logistical victory was not just an ocean of fresh cargo ships arriving from across the Atlantic. It was a standardized ecosystem that recognized a broken machine still contained life. The American system separated a 30-ton tank into thousands of interchangeable modules. A catastrophic hull penetration did not condemn the delicate radio sets, the pristine 75mm gun barrel, or the heavy steel bogey wheels bolted to the opposite side of the vehicle. The German army, crippled by a culture of artisanal engineering and constant factory modifications, could only watch as their own magnificent, damaged beasts were left by the roadside to freeze or be blown to pieces by their own retreating crews. They could clearly see the terrifying operational readiness of the American armored columns pushing relentlessly forward, but they could not see the hidden, muddy machinery making it possible. That machinery was not abstract. It was entirely composed of human labor operating in the most miserable conditions imaginable. The American system was built by the mechanics, the welders, the heavy crane operators, and the recovery drivers of the Ordnance battalions. The Shermans advancing toward the retreating German lines were not all factory-fresh replacements. Many were stitched together from the very graveyard. These men operated in the freezing rain, the deep mud, and the dark, constantly exposed to intermittent artillery fire and hidden mines. They were the scavengers of the armored divisions, armed with sledgehammers, oxyacetylene torches, and 60,000-pound winches. Their war was uniquely grim. Before a shattered tank could yield its valuable organs, someone had to wade into a crater and drag it out. Before a mechanic could salvage a perfectly functional intercom box or a pristine turret ring, they often had to face the horrific reality of what happened inside a burning fighting compartment. They washed the blood and ash of their own combat crews out of the salvaged steel, working through the trauma to ensure the next crew had a working gun. The work was exhausting, dangerous, and largely overlooked by a public that preferred the clean, patriotic heroism of the assembly lines back home. The massive factories in Detroit, Chrysler, and Fisher Body forged the steel, but the exhausted mechanics in the muddy fields of France, Belgium, and Germany forced that steel to keep fighting. They were the ones who ensured that the mechanical momentum of the Allied advance never stalled. When an American Sherman finally crossed the Rhine River into the German heartland in the spring of 1945, it was rarely the exact same pristine machine that had rolled off a factory floor in Michigan months earlier. The German gunners thought they had created. The enemy was not just producing tanks, they were harvesting them. It was a mechanical ghost. It drove on track links pulled from a shattered wreck in Normandy, fired a main gun salvaged during Marne, the freezing nights of the Ardennes, and received its tactical orders through a copper-wired radio harvested from a burned-out hull in Lorraine. It was a weapon kept alive by a shadow army of unnamed men, armed with heavy wrenches and an unforgiving system, turning the dead back into weapons. To understand how dead American machines returned to the fight while intact German machines could be resupplied, we first need to look at what exactly happened in the mud and the dark the moment the shooting stopped. When the firing stops and the front line moves forward, a strange quiet settles over a disabled tank. Rain hisses against hot armor. Smoke drifts from cracked hatches. To the crew that was just forced to bail out, the machine is dead. A shattered track, a jammed turret ring, or a pierced engine block immediately takes the vehicle out of the fight. It can no longer move, shoot, or communicate. To the men who fight inside it, the tank has failed. But disabled is merely a tactical condition. The air smells of scorched rubber, spilled diesel, and the sharp chemical bite of cordite. From the nearest hull, the metallic pop. The deeper question was how an army defined a total loss. For the German military, the classification of battlefield damage was becoming increasingly binary and unforgiving. A total loss, or Totalverlust, meant a vehicle was beyond the scope of a field workshop. If a panzer took a high-velocity impact that ignited its internal ammunition, the resulting fire burned at thousands of degrees. This intense heat warped the heavy armor plates and ruined the temper of the steel chassis. To a German officer, a burned-out hull was a tomb. It was useless. At best, a retreating crew might unbolt a coaxial machine gun or smash the optics to deny them to the enemy. The heavy mechanics, the transmission, the overlapping road wheels, the massive track links were abandoned to the rust and the mud. The American Ordnance Department looked at the exact same catastrophic damage and saw something entirely different. They did not see a single, dead machine. They saw an unharvested inventory list. The American logistical doctrine recognized that a 30-ton Sherman was essentially a steel box, carrying thousands of discrete, highly engineered components. An armor-piercing shell might punch through the right side of the hull, devastating the interior compartment, but the physical physics of the impact were localized. The shockwave and fire might ruin the engine compartment. Of heavy machine gun ammunition cooking off in the heat echoes across the sudden silence of the battlefield. But the heavy cast steel bogie assemblies bolted to the opposite side of the tank were completely untouched. The expensive, delicate copper wiring of the radio set in the turret overhang might still be pristine. The 75mm main gun barrel, forged from high-grade steel, often survived completely intact. To an American ordnance officer, a written-off tank was not a grave. It was a densely packed, forward-deployed supply depot. This was the blind spot the German gunners could not see. They calculated attrition by counting intact hulls. The Americans calculated attrition by counting available spare parts. The United States military understood that shipping a 300-pound road wheel or a 1,000-pound transmission across the Atlantic Ocean took weeks of planning, shipping tonnage, and convoy protection. But a perfectly good transmission was sitting right there in the French dirt, bolted to a chassis that would never drive again. In the cold hours after a firefight, as the infantry secured the perimeter and the surviving armor rolled forward, the wrecked machines were left behind. The fires slowly suffocated. The heavy metal cooled in the damp night air. In the German way of war, these hulks belong to the earth now. For the concealed German gun crew, this is a moment of pure mathematical certainty. They understand the brutal physics of their trade. But the American system dictated that nothing valuable would be left to rot. Knowing a ruined tank contained good parts was only the first step. Extracting them was a brutal physical problem. A severed steel track weighed thousands of pounds. A functioning turret could not be unsold and carried away by a passing infantryman. The combat troops were already miles ahead. To harvest the steel, someone had to plunge into the silent, newly captured territory and drag the corpses out of the mud. The combat troops had already pushed miles ahead, leaving the dead machines behind in the quiet dark. For a few hours, the ruined Shermans sat completely alone in the mud. Then, the distinct, rhythmic rumble of heavy radial engines echoed back from the tree line. The vehicles that emerged from the shadows did not look like fighting tanks. They were M31 and M32 armored recovery vehicles. Built on standard medium tank chassis, these specialized machines carried no functional main guns. Instead, their hulls were dominated by massive, pivoting A-frame boom cranes and heavy winches capable of pulling 60,000 pounds of dead weight. They were industrial tow trucks armored against shrapnel and sniper fire, driven by the men of the U.S. Army Ordnance Maintenance Battalions. The ordnance crews were a different breed of soldier. A 75mm armor-piercing shell striking steel at over 700 meters per second does not merely halt a vehicle, it violently shatters the interconnected machinery inside. Wearing grease-stained coveralls and armed with heavy steel cables, shackles, and acetylene torches, they operated in the immediate, dangerous wake of the assault. Their battlefield was littered with unexploded ordnance, hidden anti-tank mines, and the grim reality of what happened to the men inside the destroyed vehicles. But they had a logistical job to do. The supply lines demanded it. Moving a 30-ton steel corpse is a problem of extreme physical friction. A Sherman with a functioning drivetrain can roll easily, but a tank with a shattered track or a seized transmission becomes a massive anchor. If a track was broken, the road wheels dug deep into the soft French earth, plowing the mud rather than rolling over it. Mechanics waded into the craters, feeling blindly in the dark for the heavy steel towing pintles welded to the hull of the dead tank. They dragged thick, grease-coated tow cables through the mud and secured the massive shackles. Inside the M32, the operator engaged the power takeoff. The winch drum began to turn. The heavy steel cable snapped taut, vibrating with immense tension and shedding water like rain. The recovery vehicle's engine roared, its tracks slipping for a fraction of a second, and then the dead tank groaned. With the horrific screech of tearing metal, the wrecked Sherman was dragged backward, sliding out of its grave. One Sherman rests at a steep angle, its right track completely severed, the heavy steel links unspooled in the dirt like a broken watch spring. The ordnance crews hauled these hulks away from the artillery zones, dragging them miles backward into camouflaged farmyards, empty fields, or ruined village squares. These were the mobile triage centers of the armored divisions. Here, maintenance officers evaluated the casualties. A tank with a pierced engine block, but an intact chassis might simply receive a replacement engine. But the true write-offs, the burned-out hulls, the catastrophic structural failures, were dragged into a designated corner of the perimeter, the boneyard. In a German sector, such a pile of ruined armor would be left to rust, a tragic monument to a lost platoon. In the American sector, this boneyard was a highly active industrial zone. The wrecks were no longer tanks, they were raw material. But hauling a massive steel hull into a French pasture only solved the problem of transportation. The real challenge was mechanical. A tank is built to withstand extreme battlefield stress, meaning its components are bolted, welded, and torqued together with immense force. Once a fatal casualty was secured in the field shop, how did mechanics quickly dismantle an armored fortress to extract the delicate, high-value organs trapped inside? Dawn in the field shop. Mechanics climb over the blackened hull of a ruined Sherman. They are armed not with rifles. Another has a clean penetration through the front glacis, its internal radio sets, wiring harnesses, and optical sights presumably reduced to slag, but with heavy sledgehammers, massive socket wrenches, and oxyacetylene torches. The air smells of wet ash and burned paint. This is the operating table, and the dismantling process is systematic, ruthless, and fast. The crews usually began with the heaviest exterior components, the tracks and suspension. A Sherman's mobility relied on bolted bogie assemblies, each containing heavy steel springs and rubber-rimmed road wheels. If an armor-piercing shell detonated inside the fighting compartment, these external lower units often survived perfectly intact. Mechanics used long breaker bars to loosen the massive factory-torqued bolts. When the sheer force of a blast had warped the hull and seized the threads, the cutting torch sliced through the stubborn steel in a shower of white sparks. The boom crane of the M32 recovery vehicle then swung over, lifting the heavy assemblies clear. The tracks were harvested next. A single Sherman track was a continuous band of steel blocks weighing over 3,000 pounds. If an anti-tank mine had shattered the right track, the left side was carefully rolled out. Mechanics swung heavy sledges to drive out the steel connecting pins, breaking the heavy track down into manageable segments for future use. Next, the extraction moved to the turret. The 75mm main gun was a highly valuable asset. If the barrel was not visibly warped or pierced, it was salvaged. Mechanics unpinned the breech block from the inside, disconnecting the recoil cylinders. To the German eye, these are permanent write-offs, useless scrap metal. The crew believes they have permanently erased a platoon of enemy armor from the campaign map. The recovery vehicle's crane hooked the heavy steel tube, carefully backing away to slide the weapon completely out of the shattered mantlet. But the highest priority targets were often the most fragile. Inside the rear turret overhang sat the radio set. A modern armored offensive relied entirely on voice communication to coordinate fire and movement. The vacuum tubes, copper wiring, and delicate frequency dials could easily be ruined by exposure to the elements or the lingering heat of a fire. Mechanics climbed down into the cramped, soot-stained interior, carefully disconnecting the heavy steel mounting trays. They extracted the radio sets, the intercom boxes, and the wiring harnesses, rushing them into waterproof tents before the rain could touch the exposed circuitry. Within hours, a 30-ton fighting machine was reduced to a stripped metal carcass, its skeleton left for salvage drives later in the war. Beside it sat a meticulously organized inventory: suspension bogies, heavy track links, a pristine main gun, and functional communication gear. The Ordnance Battalion had essentially created a forward supply depot out of thin air, wiping out the need to wait for a supply ship from the United States. The salvaged parts were cleaned, greased, and immediately prepped for reuse. However, extracting these components only solved the problem of supply. The mechanical reality of repairing damaged vehicles was infinitely more complex. The American military operated multiple distinct variants of the Sherman tank,